Good evening. Trying something a little bit different. This is an idea I've had for some time. I've been meaning to try it out. I am going to try and teach a little bit of how computers work, starting from the bottom with the bits and the bytes, which is how computers represent data. So, you may have previously heard that it's all just ones and zeros. But what does that actually mean? So at the lowest levels of computation, all you have is fairly basic mathematical operations. And all of those mathematical operations happen on numbers. And all of those numbers are represented as binary data. What you may be used to from your mathematics classes in school is numeric representation like this. This is the number 134. However, computers don't represent numbers in this way. We call this representation here base 10 because each digit has 10 separate values from 0 all the way up to 9. There is no 10 because the 0 takes up a number. Let's say we wanted to try something different, and instead of 0 to 9, we just wanted to use 0 and 1. This is a counting system called base 2. So where in our previous 1, 3, 4, we have the rightmost or least significant digit representing 4 multiplied by 10 to the power of 0, because it is in the 0th position, which is 4 multiplied by 1, or simply 4. Now with the 3, what we have is, let's get rid of this, we have the 3 multiplied by 10 to the power of 1, or 3 multiplied by 10, or 30. That's a 0. My writing is... It leaves a lot to be desired. And then... Oh, whoops, I shouldn't have erased the 1 through 4. I'll put it back. Then the 1 is multiplied by 10 to the power of 2. Or 1 multiplied by 100. Or just 100. So each digit contributes to the value based on its position. So positions go from 0, 1, 2, right to left increasing. And this is all transferable knowledge to base 2. So let's take an example base 2 number. 10. Wait, no, it's not 10, it's 1 0. we don't say 10 in binary 1, 0. So we have 0 multiplied by 2 to the 0, which, as we know, is 0. Then we have 1 multiplied by 2 to the power of 1, so 1 multiplied by 2, which is 2. So 1, 0 in binary is 2. Let's try something slightly more complicated. One zero zero 1 0. So let's break this down as we have 0 here. We won't bother doing that calculation, but so let's label the positions here. So we have a contribution of 1 multiplied by 1 to the power, 1 multiplied by 2 to the power of 1, plus 1 multiplied by 2 to the power of 4. This is 1 multiplied by 2 plus 1 multiplied by 2 to the power of 4 is 16, because it's 2 multiplied by 2 multiplied by 2 multiplied by 2. 16. 2 plus 16 is 18. So we say that this is 18 represented in binary. Now, if you are a little confused at this point, I do recommend rewinding back and seeing if you can follow the second time around. The key to this is to not think of decimal numbers at all, but to realize that decimal, or base 10, is a numerical system in which each digit contributes its numeric value multiplied by 10 to the power of its position from right to left. So we end up having 1 multiplied by 10 to the 2 plus 3 multiplied by 10 to the 1 plus 4 multiplied by 10 to the 0th power. So why base 2? Why not base 10? At the hardware level, computers are electrical currents, and a circuit board. Let's try and draw a very basic circuit board. Now, it's probably at this point that I admit that I do not know huge amounts about hardware. My specialty is software, but I do have a basic understanding. I just can't promise that this will be an accurate drawing. It's just going to be a very kind of like showy circuit board, but they all kind of like, you have these silicon lines running around, and you have joints which are soldered, and then these lead to other components on the circuit board, and you've got fuses and all kinds of things, right? The thing to note is that electricity runs through the lines on the circuit board, and when it does, it carries either a high or a low current. Those are the only two options. So all of the counting that computers end up doing involves two distinct values, and so everything is counted in base 2. Now, I mentioned at the beginning of this video that we have bits and we have bytes, and that's what we're covering today. So a bit in computer speak is a single digit in base 2, either a 0 or a 1. That is a single bit of data, that two potential values. Now, a byte is just 8 consecutive bits. For example, 1, 0, 1, 1, 0, 0, 1, 1. We have 0, 1, 2, 3, 4, 5, 7. So 1, 2, 3, 4, 5, 6, 7, 8 bits. And this is a byte. The maximum value that a byte can hold is 2 to the power of 8 minus 1. Now, what is 2 to the power of 8? Well, there's a little cheat that we can do here. 2 to the power of 10 is the first power of 2 that exceeds 1000, which is 1024. In general, every 10 powers in 2, so 2 to the 10, 2 to the 20, 2 to the 30, typically will be the first value that crosses a threshold. So 2 to the 20 is the first value that goes over 1 million, and so on and so on. So all we need to do to get 2 to the 8 is divide this by 2 twice, which gives us 2, 5, 6. Because 1024 halved is 512, then 512 halved is 256. Then subtracting 1 gets us 2, 5, 5. This is the maximum value you can represent in 8 bits. You may be thinking, why do we subtract 1? And the reason for that is that 0 is a value. So why do computers care about 8 bits? Why do they care about bytes? What's so important about that? Now, there are little bits of history involved here that, honestly, I don't know in detail, but at some point in the distant past, we standardized on a byte being 8 bits. In some computer systems, a byte was 7 bits, but that isn't the case anymore, and I don't know why it was changed. I get the feeling 8 is a little bit easier to reason about, because it itself is a power of 2. Remember, 8 is 2 to the power of 3. 2 multiplied by 2 multiplied by 2 equals 8. So the byte is the fundamental smallest unit of memory you can access on a computer. Now, what do I mean when I say memory? You may have seen computers advertised to have 16 gigabytes of RAM. Now, RAM stands for Random Access Memory. And 16 gigabytes is 2 to the power of, now let me think about this. I think it's 2 to the power of 34 bytes. And the cheat that I did there is that I know 1 gigabyte is 2 to the power of 30. And then if you double it 4 more times, you get 16. Because you do the 1, 2, 4, 8, 16. So that's 1 double, 2 doubles, 3 doubles, 4 doubles. So random access memory is a fundamental component in computer systems. When you turn on your PC, the first thing it will do when it loads your operating system is it will read it in from your hard disk and load it into your random access memory. And there are a number of reasons that it does this. The most important reason is that your CPU cannot talk directly to your hard disk. Even if it could, you wouldn't want it to, because your hard disk is approximately 1 million times slower than your random access memory on average. The other reason is... oh no, sorry, I covered that, whoops. It's because the RAM is significantly faster than your hard disk, and your hard disk cannot be accessed directly by your CPU, whereas your CPU can access RAM. And the CPU is the thing that does all of the basic arithmetic operations that we were talking about earlier in the video. Addition, subtraction, multiplication, division. All that a computer does fundamentally is these things. And then other bits of hardware interpret the results accordingly. As a practical example, a pixel on your screen is a single dot of color. So if you had a 4x4 screen, you would have 16 pixels. Now, in reality, screens tend to be 1920 by 1080 pixels or larger these days. So they have much more pixels than our example here. But let's say, for example, one of your pixels is red. You have another pixel that is green. Then another pixel that is blue. How does this relate to bytes? Well, each color value on your screen is represented by a set of 3 bytes. 1 byte representing red, another byte representing green, another byte representing blue. So a pixel will have between 0 and 255 strength red, between 0 and 255 strength green, between 0 and 255 strength blue. So our red pixel would be 255 0 0. Our green pixel would be 0 255 0, and our blue pixel would be 0 0 255. And to get other colours, you would mix in various different values in there. However, colour values aren't typically written like these here, because that is just a little bit too much writing. Instead, the way that we write colour values is in yet another counting system called hexadecimal. Now, hexadecimal is a counting system that ranges from 0 to 15. So whereas in base 10 we have from 0 to 10, base 2 we have 0 to 9, base 2 we have 0 and 1, in hexadecimal we have 0 to 15. However, we don't typically represent the final values as 2 digits. Instead we start using the letters. So in hexadecimal we use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we use A, B, C, D, E, and F. And that is 0 to 15. And it works in exactly the same way that base 10 and base 2 do, in that each position contributes the position multiplied by the value in that position multiplied by the base to the power of the position. So red ends up being F, F, 0, 0, 0, 0. Because 255 is represented by the highest possible value in 1 byte. So each byte is represented by 2 hexadecimal numbers. And then you have no contributions for the other bytes. And it's the same with green. Just have FF here. And then with blue, you have 0, 0, 0, 0, F, F. And this is a really neat way of writing binary, bytes, really. Because each byte is very neatly represented as 2 hexadecimal digits. Now, we have gone all the way up from the humble bit, 0 and 1, to bytes, to multi-byte sequences that represent some real-world concept. And the monitor that you are watching this through, or the screen on your phone, will be interpreting many, many 3-byte sets to determine the value of each pixel on the screen. And it will be doing this possibly 60 times a second. So if you are kind of further interested in this world of numbers and colours and low-level binary data that computers deal with, there is a wonderful stand-up comedy routine by Matt Parker of Numberphile fame, where he does these kinds of numeric color representations in an Excel spreadsheet, and he really well demonstrates with a microscope what screens look like. Now, sadly, I don't have a microscope. I wish I did. Maybe I'll get one for a future video or something, but I will link to Matt Parker's video in the description. There's just one final thing I would like to cover, and that is, if computers deal exclusively with bits, bytes, and numeric information, how do we represent text? The answer is simpler than you might imagine. We just represent letters as numbers. There's not much more to it than that. There is a standard mapping from numbers to letters called ASCII, A-S-C-I-I. Now, I can't remember what this stands for. I think the two I's stand for information interchange, and I think the A stands for America. It's something like the American Standard something for information interchange, something like that. And this is a standard that for every value of a byte, it will map it to a letter or a symbol or something of that ilk. There are some special characters that aren't used so much anymore, but some frequent ones that aren't used, for example, are when you go from one line to a new line, that is actually an ASCII character called the Newline Character. And that's how programs such as Word or Pages knows to go to the next line. It will encounter a Newline character, which, and now I forget what number it is. I don't know the numbers off the top of my head, except I think capital A is 61. But I could be wrong. It's just a guess. And this is all well and good for English. You can easily, sorry, I say English, I mean Roman languages with Roman alphabet. You can fit the entirety of our alphabet in uppercase and lowercase in the 0 to 255 range, but it falls down when you need to represent other languages that have much larger character sets, or for example if you want emojis, because each emoji is numeric information as well, which is why we also have something called UTF. I don't know what it stands for, but it has a bunch of numbers after it as well. So there is UTF-8, UTF-16, UTF-32, and honestly, in 2018, we don't use these anymore. The number at the end represented how many bits it used for each character, but the nice thing about UTF-8, which appears to have won in the war to decide the best way of representing characters as numbers, is while it has an 8 here, which suggests it uses 8 bits for every character, it can actually use as many bits as it likes. The encoding is, one of the things that it specifies is for each byte it encounters. If the most significant bit is a 1, it will assume that it must also read the next byte to determine what the character is, and this ends up being what's called a variable length encoding. And you can represent an arbitrarily large number of characters with it, which I think is part of the reason it has won out over the other standards. It also means that the language of the internet in the Western world, which is primarily English, can be represented using quite small numbers of bytes, because most of the alphabetical characters like A to Z have a 0 as the starting byte, so each character is represented as only 1 byte when American or British English are considered. So you end up with quite small representations, which is efficient in data usage. That is my first video on how computers work. I intend, as time goes on, to make many of these and try and build on the previous ones as I go along. So, thank you for joining me, and I will see you again very soon.